Hi there and welcome to the Inner Loop. In this episode we're going to talk about these things. We're going to talk about plucking strings. We're going to talk about how I coded it and some of the challenges and some of the interesting things that I've learned about musical instruments. Oh! How do you get a computer to simulate a string that's going twang? I've modelled it as balls and springs. So you have balls and they're connected by springs. I wish the dogs would stop barking. As you can see, every time I try and explain this, the other dogs start barking or I lose my train of thought. So let's just go on with it. Here's the code running, and we can watch what happens when we just pluck the string. As this simulation is running along, the time is speeding up. So you're starting to see the whole waveform, but in a short time. Where you pluck the string makes a difference. If you pluck the string exactly in the middle, then it's going to encourage the first harmonic. The whole string is going to go up and down like that, because that's where you plucked it. If you pluck it towards one end, then what's going to happen is it's going to send a ripple, like a wave, up and down the string, and you're going to get maybe higher harmonics. So that's the first thing I tried with the code, is like, let's try plucking it in different places and see what it sounds like. So here you're actually going to hear something. So how am I going to tune this? You can tune a guitar by either increasing the tension, or using a thicker string, or by changing the length. For me, the first thing I did was to choose a mass for the string, and then tune it by changing the length. And I found this really cool online spectrum analyzer. So let's look at all the different strings that you have in a guitar and their frequency spectrums and what they sound like when you pluck it. And all together, they sound like this. There's a wonderful number in music, which I've now discovered, which is the 12th root of 2. Every note in music then follows the next by a multiple of the 12th root of 2. So once you've played 12 notes, you've got to the next octave, because you've multiplied the 12th root of 2 by itself 12 times, which gives you 2. And that's the number that I use to calculate the frets, where the frets need to be. That's the distance or the length of the string. Let's listen to some notes. The frequency of a vibrating string is proportional to 1 over the square root of the mass of the string. So if you make the string 4 times heavier, it will go down only 1 octave. It'll go down by half. But the mass is actually proportional to the thickness squared, because the area of the string is pi r squared. So actually the the frequency of the string is proportional to the thickness of the string, or 1 over the thickness. So if you make it twice as thick, you'll get half the frequency. So that was how I managed to tune the different strings in the code. I just used that magic number again, the 1 over the 12th root of pi, the 12th root of 2, for each semitone multiplied by the square root of the mass. So once I tuned one string by getting the length right, or the number of balls and springs, I then had all the other strings came into tune. Let's listen to a tune. In the code, I wrote a very simple sequencer that can read guitar tabs. You've got to type them into a text file and it just plays it. So that's how I played the tune. I also did the theme from the Deer Hunter, but if I play too much of that, I think I'll get a copyright strike. So I'll play a little bit, and then we'll move on to the next question. Does it play bass? So what happens if you disconnect one end? Make a kalimba. Oh, not so successful. The reason being that the loose end, if you ever had a string, you take it off a guitar, you can't pluck it because you need some tension in the string. You can have a loose end, but I need to model it as a 2D object rather than a single line. So no kalimbas in this video, I'm afraid. What about one of these? Can't be too hard, because as long as it's excruciating, you've succeeded. The thing about a violin is it's all about the plucking mechanism. I didn't have to change anything in the code other than plucking is, instead of just whacking the string once, it's whacking the string randomly. But I think violin strings are subject to both static and dynamic friction. So if you try to play a violin with a piece of sellotape, it's just going to slip over the strings. The thing about the bow, I think, is it digs in. So when the difference in velocity between the bow and the string is low, it will push the string on. But when there's a fast velocity in terms of it's going the opposite way, the dynamic friction is much lower, and the bow just jumps over the string. So that's what I coded. If you've got a low difference in velocity, you can increase it. If you've got a high difference in velocity, or it's going in the opposite direction, just leave it alone. What does that sound like? This has been a bit of a whistle-stop tour through quite a lot of time and effort that I've spent coding this thing. I'll put the code on my GitHub because I was trying to explain it, but it's probably just easier for you to have a look at it if you're interested in code. The final thing I was looking at is one of these. But along with the kalimba, I need to model maybe either a rectangular or circular plate, and I also need to model something which has some depth. some more dimensions. I might look at that in the next video. If you've got any questions or comments, or if you want to send me a guitar tab, I'll see if I can play it for you. Thanks ever so much for watching, and I'll see you next time on the Inner Loop.